Let's investigate the von Neumann entropy. First, let's define the density operator rho as the sum over some index k of probabilities p sub k, which are the coefficients of ket-bra combinations constructed from the states labeled by psi sub k. So each ket-bra combination in Dirac notation is a projector. And we are taking a linear combination of these projectors, and the coefficients in this linear combination are probabilities, p sub k. This describes a mixed state in general. And in the special case, where we're only dealing with one of these ket-bra combinations, we only have a single projector associated with a state, that is called a pure state. And you can see that a pure state is a special case over here, where this index k only has one value. And in that case, p sub k is equal to 1. There's a 100% chance of the system being prepared in that pure state. But we have to generalize to mixed states, because mixed states are a lot more realistic in describing quantum mechanical systems. So this density operator can be diagonalized. We can express this in another basis. We can express this as the sum over some index j of lambda j times the ket-bra of these states which are labeled by j. And you can see that we still have the same operator, we're just expressing it in a different basis. And we're choosing the eigenbasis of rho. So we need to find the eigenvectors and the eigenvalues, and then we can transform into a different basis where the matrix representation of rho is diagonal. So in general, if we express rho in some arbitrary basis, it's not guaranteed to be diagonal. But we want to deal with a diagonal matrix. So we want the matrix representation to only have non-zero entries along the diagonal. And all the other entries in the matrix need to be 0. Now, the reason for this is because diagonal matrices are very convenient to do computations with. A non-diagonal matrix, which has entries off the diagonal, that can be very tedious when you're putting it into a function that takes matrices as inputs and splits matrices as outputs. So we're going to see that later in this video. Now, what we can do is we can construct a matrix representation from this. So this over here is actually a matrix representation in disguise. We can write this as a diagonal matrix. So we'll put capital D for diagonal. And the entries of this diagonal matrix are lambda 1, ... all the way up to lambda sub capital N. And this capital N is the dimension of the Hilbert space that we're dealing with. So this notation over here is for a diagonal matrix. So this is the matrix representation of rho in this basis, which is the diagonalized eigenbasis. So these lambdas over here, you can think of them as eigenvalues. And this j over here, it is just a label for each of the states that form this eigenbasis. Now let's apply a function to this rho over here. So let's take rho as an input to a function. And let's consider the function rho log rho. So this is a function that inputs a matrix and it spits out another matrix. So this ln over here, that is the natural logarithm. Now it might be unusual to see the logarithm of a matrix, but it is possible to define such an operation. So we can take exponentials of a matrix, and we can also take logarithms of matrices as well. One way to define the exponential of a matrix is with the Taylor series for the exponential function. So we can think of this as a polynomial that just keeps going on and on forever with higher powers of the matrix. That is what an exponential of a matrix means. And when we take the logarithm of a matrix, we're doing the inverse. We're finding what matrix had to be there to produce the exponential of a matrix. So that is what this log of rho means. So if this matrix is not diagonalized. It would be very tedious to perform this operation. But if we get it in a diagonal form, then all we have to do is apply this function to each of the entries along the diagonal. So this over here, if we deal in this diagonal basis, is going to give us the sum over j of lambda j log lambda j. So we're just taking each of these diagonal entries and we're substituting them into this function. And then we also need this ket-bra combination. And this ket-bra combination tells us that we're just dealing with entries along the diagonal. So this index is the same in both the ket and the bra. And that corresponds to the diagonal entries. Now, what would the matrix representation of this look like? Well, it's very similar to what we have up here. We will have a diagonal matrix, so capital D for diagonal, and then the entries will be lambda 1 log lambda 1 and dot 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 all the way up to lambda n log lambda n, and that's the final entry. And this capital N is the dimension of the Hilbert space. So if we're dealing with just a qubit system, then we're just going to have two entries over here. It's going to be 2 by 2 matrices, and there's only going to be 2 entries along the diagonal. But if we want to generalize this to an n-dimensional Hilbert space, we need all of these entries. So you can see why diagonalization is so useful. It allows us to conveniently do operations to matrices. So now we just have to know what the entries, or these eigenvalues are in this diagonal matrix, and then we can substitute each of those entries into the function, and that gives us the result of this function, which inputs rho. Now, why did I choose this specific function? Well, it's because this function is going to allow us to define the von Neumann entropy, which I will write as S of rho. So the von Neumann entropy, S, of the density operator rho is defined as minus the trace of this quantity, rho log rho. So this is our definition for the von Neumann entropy. And what is this going to be equal to? Well, we already know what the matrix representation of this operator is. We know what this is. And now we just have to take the trace. And the trace is just going to be the sum of the diagonal elements. So that's going to give us minus the sum over j of lambda j log lambda j. So this is what we have. We do not need to write this ket-bra because this ket-bra, this is a projector. These are operators. We're using these ket-bra combinations to construct an operator. So this is an operator, this is also an operator. And then we have matrix representations of these operators in a particular basis. But this over here, this is a number. This is a numerical value. And we don't need any ket-bras over here. We are just summing values. So we're summing all of these values. And this j, that is just the index which tells us which value along the diagonal we're dealing with. Now, this format for the entropy is very familiar. You might have seen this in statistical mechanics. In classical statistical mechanics, we can define the Gibbs entropy, which I'll write as S sub G. This G over here is just to distinguish from this von Neumann entropy. And we can write this as minus Boltzmann's constant, which is KB, times the sum over some index, let's call it I, Pi log Pi. So these P's over here, which are labeled by the index I, they are probabilities. And we have this same format where we have a probability times the log of a probability. And we're summing over the index, and there's also a minus sign out the front. So this format is very similar to this format for the von Neumann entropy. The notable difference that you will see is the presence of this constant out the front. So this is Boltzmann's constant. Why do we include this constant over here? Well, it's because entropy was originally discovered in thermodynamics. So we were interested in quantities like energy and temperature. And this constant over here has the dimensions or the units of energy per temperature. In SI units, that would be joules per Kelvin. So putting this constant over here gives this quantity of the Gibbs entropy, the same units that we want when we're dealing with thermodynamics. So thermodynamics is explained by classical statistical mechanics. And that is where this quantity emerges, in classical statistical mechanics, where we're dealing with microstates and macrostates. So these probabilities over here are analogous to these lambdas, these eigenvalues. So this is how we go from classical statistical mechanics to quantum statistical mechanics. So here we have von Neumann entropy. Now let's have a look at some properties of von Neumann entropy. So one very interesting property is that the von Neumann entropy is equal to 0 if and only if rho squared is equal to rho. Now what does it mean that rho squared is equal to rho? Well, that's the case of a pure state. So just as we were talking about only one of these Ket-Bra combinations existing in this linear combination. So if the probability is equal to 1 for just one of these Ket-Bras, then we're dealing with a pure state. And that pure state is a projector. It's represented by a projector for this density matrix. And a projector satisfies this relationship. The square of a projector is equal to itself. So if you apply a projector twice, it's the same as applying the projector once. Now, another way of quantifying this or summarizing this is the purity is equal to 1. So the trace of rho squared is equal to 1. If you take the trace of both these guys, the trace of rho has to be equal to 1. That's the normalization condition. So that means the trace of rho squared is also equal to 1 for a pure state. Another property is that it is Hermitian, because if you have a single Ket-Bra combination and you take the Hermitian adjoint, you swap the Ket and the Bra, and that has no effect. In general, it will have an effect. But in this special case over here, it doesn't have an effect because we're just exchanging the Ket and the Bra. So this is the special case of zero entropy. So the entropy is equal to 0 for a pure state. Now let's have a look at another interesting property. If we sandwich rho between some unitary operator, u and u dagger, this is the same as transforming it into a different basis. And then we take the entropy of this combination. It doesn't actually change the entropy of rho. So the von Neumann entropy of rho is the same as the von Neumann entropy of a transformed version of rho, if we're transforming with a unitary operator. So this is u and u dagger. They're acting from the left and from the right. So if we look at this definition, u is going to act from the left on the Kets, and u dagger is going to act on these Bras from the right. So this is a very interesting property. Another very interesting property is what are the bounds for this entropy? Well, if we consider the maximally mixed state, the entropy is going to be the log of the dimension of the Hilbert space. So that is the maximum value that this entropy can have. And the minimum value is going to be 0. So that corresponds to this pure state over here. And we can observe that this is also described by the purity. So the purity for the maximally mixed state is 1 over n. And that is the lower bound of the purity. The purity is defined as the trace of rho squared. And the upper bound for the purity is 1. So we can see here we're dealing with the purity, and here we're dealing with the von Neumann entropy. This value over here corresponds to a pure state, and this value corresponds to the maximally mixed state. You can see that these less than and equal to signs, they are swapped over. So over here, we have this guy sandwiched between these values, and over here we have this guy sandwiched between these values. So this would be the maximum, and this would be the minimum over here. So let's see why this is true. Let's consider the maximally mixed state. So the maximally mixed state, I'll write as rho sub m for maximally mixed. This can be expressed as 1 over n times the identity matrix, which is n by n dimensional. So if we were dealing with a qubit system, this would be a 2 by 2 identity matrix, and this coefficient would be 1 on 2. That's 1/2. Now let's take the trace of this value. So if we take the trace of rho m, that is going to be equal to we're going to have n copies along the diagonal, and each of those entries on the diagonal are 1 over n. So we're going to have n times 1 on n, and that's equal to 1. So that is the trace of rho m. This just means it satisfies the normalization condition. Now let's take the trace of rho m squared. This is the purity. That's this quantity over here. Now what is that equal to? Well, if we square this, the identity squared is not going to be affected. But if we square these coefficients over here, that's going to give us 1 on n squared. So along the diagonal, we're going to have n copies of 1 on n squared. This n over here is because there are n entries along the diagonal, and this 1 on n squared, this is the value of all of those entries. So that means this is just going to give us n over n squared, which is the same as 1 on n. And that is where this lower bound comes from. Now let's calculate the von Neumann entropy. So the von Neumann entropy of this maximally mixed state is going to have this format. So how many values are we going to have in this sum? Well, I'll put a minus sign at the front. We're going to have capital N values, just like we have capital N values of this matrix over here. That's how many entries we have to sum over. Then, what are all the entries going to be? Well, we need to consider this matrix over here. All of these entries are going to have this form. And all of these lambda j's, they are going to be 1 over n. So what's that going to give us? Well, we're going to have 1 over n times the log of 1 over n. So you can see this format, it's the same as this format over here, and this format over here. And we have a minus sign at the front, and this capital N over here is just how many copies we have along the diagonal. So this n and this 1 over n are going to cancel, and this minus sign, we can bring it inside and flip this, take the reciprocal inside the log, and that's going to give us the natural log of n. So the natural log of n, that is this bound for the von Neumann entropy. So now we've seen where these values actually come from. So 0 is the case for a pure state, and the log of n, that is the case for the maximally mixed state. And the other values for the entropy are for some arbitrary mixed state. And over here we have the purity, and the purity also gives us some information. So over here we're dealing with a pure state, and over here we're dealing with the maximally mixed state. Now that we've seen the von Neumann entropy, and we've also compared it to the Gibbs entropy over here, let's define the Shannon entropy from classical information theory. So I'll define that down here. The Shannon entropy, which I'll write as H of some discrete random variable capital X, that is equal to the expectation value, I'll use this symbol for the expectation value, of minus the logarithm base b, so we have a logarithm with some arbitrary base, which we can choose, of p of this discrete random variable x. So these are probabilities, and this is minus the logarithm. This quantity inside this expectation value is actually given the name information content. You can think of this as the information content. And if we take the expectation value of this quantity, that can be written as minus the sum over little x. So these are the possible values that this discrete random variable can have. And then we need the probability of little x times the log, given this base, of the probability of this little x. And you can see that this format, now that we've taken this expectation value, this format is the same format that we're dealing with for the von Neumann entropy and for the Gibbs entropy. We have these probabilities, we have this format where we have minus the sum over a probability times the log of that same probability. So that's this format that is showing up in different areas of physics. It's showing up in quantum mechanics, it's showing up in classical statistical mechanics, and it's showing up in information theory. So what can this b be? What are the allowed values for b? We can choose whatever base for this logarithm is convenient. It's the same as just changing the units of the entropy. So a common choice for b in information theory is 2. So if you're dealing with bits, then you would want to set b equal to 2. Then you can very easily take the logarithm of powers of 2. But another choice, which is really common in physics, is base e. So that's Euler's number. And if you put base e in this logarithm, that's the same as taking the natural logarithm. So that's what we have here. In this definition of the von Neumann entropy and the Gibbs entropy, we're dealing with the natural logarithm, which has base e. And another common choice is a base of 10. So you can have log base 10. And that's very useful if you are dealing with orders of magnitude and you want to recognize that these orders of magnitude are powers of 10. So these are very common choices for the base. And it's exactly the same as just changing the units of this quantity over here. And let's consider a very special case of this information theoretic conceptualization of entropy. So let's consider the binary entropy. I'll write that as H bin for binary. And this is specified by the probability P. So because we're dealing with binary entropy, there's only two possibilities. So we can express this as minus P log P, and this log can have whatever base we want to choose. And then we can have minus 1 minus P times log of 1 minus P. So this is the form of binary entropy. And the shape of this graph, if you're to plot this entropy as a function of P, is a bump. And this entropy is 0 when the probability is equal to 0, and it's also 0 when the probability is equal to 1. And it has a maximum right in the middle. So when P is equal to 1/2, or 0.5, this attains a maximum. And let's see what that maximum is. If we substitute 1/2 into this, we're going to have 1/2 here. So we're going to have minus 1/2 log of 1/2. And then 1 minus 1/2 is also 1/2. So we can see some symmetry over here. It's a symmetric graph if you plot this out. And then we have log of 1/2 over here. So we have two copies. That gets rid of this factor of 1/2. And we can move the minus sign inside the log. And that's the same as taking the reciprocal. So we end up with log of 2. So log of 2, that's our maximum value. So this is very similar to the maximum value that we have over here. We're taking the log of the dimension of the Hilbert space. But over here, we're defining this in terms of the natural logarithm. And when we're dealing with bits, it would be more convenient to use log base 2. And if we use log base 2, then this is just going to be log base 2 of 2, which is equal to 1. So that's why the base is very convenient in information theory if you choose b equals 2. So this is the binary entropy, which is used a lot in computer science and in classical information theory. This is the Shannon entropy, which underpins all of information theory. And over here, we've got the von Neumann entropy and Gibbs entropy. And these are very useful definitions in classical statistical mechanics and in quantum information. So we've seen how this density operator works, and we've seen some very useful properties of that density operator. And we've used that density operator to define a natural extension of the concept of entropy into quantum mechanics. So one last thing that I want to do is I will draw a little plot of this binary entropy over here. So we can draw it as a bump. It's a symmetric bump. And this axis down here tells us the probability. So the probability goes from 0 to 1. That's the interval that we're using. And over here we have 0.5 or 1/2. And that's where the maximum occurs. And this vertical axis, this is H bin, the binary entropy. And this value up here, all right, this is 1/2 times the log, or not times, but the other coordinate is log of 2. So these are the coordinates over here of the maximum point. So over here, we're dealing with this point in the middle, and that gives us the maximum value for this entropy. So 1/2 is this horizontal coordinate, and this vertical coordinate is log of 2. And I'll just label this axis as the probability. So hopefully now you can see how this quantity of entropy shows up everywhere, and it's incredibly useful for describing the behavior of a system and giving a quantifiable value that you can use to describe how much knowledge you have about a system. So we will be using the density operator to define other properties also in the quantum mechanics playlist.